Recording. Okay, so a quick reminder that this is a non-competitive space. CEBA is a membership organization. We emphasize that this is a space where we can all learn and grow together and avoid any antitrust behavior. So any questions on that, feel free to drop a note to me in the chat. So what is CEBA? If you're not a CEBA member and you're joining us and haven't heard of us, welcome. We're excited to chat with you. CEBA is the Clean Energy Buyers Association. We are a business association, and our work is all about just activating a community of energy buyers and their partners to advance low-cost, reliable, carbon emissions-free global electricity systems. We are have very fortunate to have over 400 member companies comprising about 1/5 of the Fortune 500 and more than 33 trillion in market cap within our membership. And it's really through our members that we are able to help shape national and global clean energy. And so we're excited to continue that conversation here today. I'm really excited about the speakers we're bringing. You're going to hear a depth of and breadth of information from AJ Simon, who is Director of Industrial Decarbonization at Carbon Direct, Roger Ballantyne, President at Green Strategies, and James Hanahan from Calpine. So you have a developer, you have consultants, you have experts in the greenhouse gas accounting space who've worked with businesses. So a great place to both learn and ask your questions. So with that, Roger, I'm going to hand it over to you to get us started.
Go ahead and go to the next slide. So I thought I'd start just with a little bit of context setting before we turn to the CCS specific discussion. And this is information I'm sure just about everyone is quite familiar with. This is a 100-year snapshot of load in the US. You can see for the past 25 years, we've been relatively flat, and that is changing dramatically as we see current and projected uptakes and demand of quite significant nature, near historical rates. And to put numbers to what most estimates are saying for the next 25 years, we could be adding as much as 2,000 terawatt hours of demand. And to put that in context, that's the equivalent of adding 40 New York cities to national load. Okay. Next slide. Now, this is a story everyone's heard, but let me just say it is not, that increase in load is not just a data center story. We're also seeing demand from electrification of buildings and mobility in an industry. But it's hard to argue that data centers and AI are not at the heart of this increase in load. To put it in nearer terms, because when we're talking about CCS, one of the messages you're going to hear today very clearly is that this is a now opportunity and not just a future opportunity. We are looking at, from various predictions in the neighborhood of digital infrastructure, adding the equivalent of four New York cities in the next 5 years. So this is a near-term phenomenon that's happening and is projected to continue on for the next 25 years. Okay, next slide. So now turning to CCS. So that context helps us understand why we're doing this now and why we're talking about CCS now. It is true that at the moment, you can see on here, there's more solar under construction than any other form of generation. If you go out to current planned projects, we start to see natural gas take over that. And the fact is that the main reaction that we're seeing from the power sector right now in response to and anticipation of this increase in demand is to deploy more natural gas. Yes, we suspect and we hope, many of us, that in the future that marginal new generation mix is going to change, particularly as we bring new technologies into the fore, maturing up geothermal, modular nuclear. We expect these technologies to grow and to come into play, but probably not for a few years. And it's just important to note that even if we bring on new generation like that into the mix and those become new marginal additions to capacity, they're not going to do anything to displace these assets that we are building today and in the near term. Those are long-lived assets, the emissions of which are going to be locked in for a long time. That's why we're talking about CCS, because either having it designed into near-term new generation or retrofitted onto existing generation. CCS is one of the few tools we have to get at those emissions that are being locked in from this infrastructure today. Next slide. So high-level advantages. You'll hear the reference many times today. This is clean, firm, and dispatchable generation, which any grid at any time needs, and in this rapidly growing grid becomes even more critical, particularly given the nature of the demand that's being added to the grid. CCS is scalable. We can do it at hundreds of mega. You can do it at almost any size, but the economics really start working in the hundreds of megawatts up to gigawatt size. So this is a large scale technology with large scale opportunity. CCS has broad but not universal geographic suitability. You do need to be within range of storage resources. But right now, even without a particularly enormous build out of CO2 pipeline transportation infrastructure, you can do this in the Midwest. You can do it in California. You can do it in Mountain West. You can do it in the Great Plains. There are many geographic opportunities to deploy CCS. And finally, as I said, what is unique about CCS is the ability to retrofit existing assets and getting at those emissions, direct reduction of emissions and not just displacement of emissions. Key advantage. Okay, next slide. But of course, yes, there are challenges and risks. Carbon capture technology is proven, it's mature, it's been around for a long time, but we haven't deployed it at scale on natural gas generation. So there is some first of a kind risk present in these transactions. And that will be a consideration and challenge in getting them built, commercialized, and fully trusted. But those are steps that we think are a very natural progression. AJ can talk to this much better than I can, probably James as well. Economic, these are large capital intensive projects. So they require a lot of capital and may, from the switching around to the offtake and buyer perspective, may require multiple off-takers for a single project. I'm just going to spend a second and then I'm going to hand it over to AJ on reputational issues because we get this question a lot. There is a growing consensus movement around CCS in the scientific community, environmental advocate, and climate advocate community. The IPCC has made very clear that carbon capture is going to need to play a significant role if we're going to meet our mid-century decarbonization timelines. So there's growing support for CCS. Part of that has to do with CCS, has been talked about for a long time, but again, that context I talked about in terms of rapidly increasing load and the lock-in of emissions from new gas assets, that's changing. That's not to say there aren't critics. There are critics of CCS. There are those who don't want to have anything to do with anything fossil, and it's really as simple as that. There are others who believe and advocate for a strategy to decarbonize the grid really just with wind and solar and transmission and batteries. And then, last point I'll make on this point is there are some even CCS supporters who are very wary of associating themselves with a CCS plant when the CO2 taken from that plant is used for enhanced oil recovery. That's understandable. and there's widespread concern about that, despite the fact that the CO2 in an EOR operation is every bit as permanently sequestered as it is in a geologic saline aquifer type of situation. And given what most economists, oil and gas economists will tell you is that an incremental barrel of oil produced by a anthropogenic CO2 EOR is not a new barrel. It displaces a barrel produced in another way. Nevertheless, fully understand there's concerns around that. But we think the overall kind of social license around CCS is getting quite strong. And I think I'm kicking it over to my friend AJ.
Absolutely. Thanks, Roger. I'm going to flip to the next slide there. Since Roger gave us a bit of background about the need for clean, firm power and the high level opportunities and risks, I want to take a step back and talk about what CCS really is. What does it look like? How does it work? So, quick orientation. When we make electricity from natural gas today, we combine the gas with air in a turbine and produce an exhaust stream that's mostly hot air and about 5% CO2. It's compact, it's reliable, it's affordable, it's pretty clean. It doesn't release a lot of hazardous air pollutants, but the CO2 is a contributor to climate change. And the technology exists, as Roger said, it's mature technology that's been tested, refined, and scaled up over the past 25 years to continue to make power from natural gas and avoid releasing most of the CO2. That's carbon capture. So the diagram you're looking at right now from the folks at GE Vernova is a regular natural gas power plant. And that tiny white box in the center, circled in orange there, is where most of the power is made. Along with all the other stuff in the picture, this plant can output about 250 megawatts. For friends of SEBA here, that's about the same as 100 wind turbines on a perfect day. But this plant can deliver firm energy around the clock. The machinery just to the right of the turbine is a steam generator used to make extra power, and the exhaust stack, which is all the way over on the right side of the picture there, that usually releases all that air with 5% CO2. So we'll flip to the next slide here. A power plant with carbon capture would look like this. It would reroute that exhaust through that really tall white cylinder that's on the far right of the new picture, and the air that was in that exhaust that now contains not 5%, but less than 0.5% CO2 is released from the top. So what happened to the CO2? I think if we go to the next slide, there we go. It got absorbed into a chemical solution and then desorbed as a pure gas inside that small cylinder at the top right. From there, it gets compressed, then shipped to a storage site and pumped underground. Let's take just a little bit longer here and note that adding all of that CCS equipment basically doubled the size of the plant. And so when we do this, we're adding a lot of material, we're adding a lot of cost, and we actually need some more energy to run all of that equipment. We talked about compressing and shipping off the CO2. Let's talk about what happens there on the next slide. A CCS project needs to look at the entire CO2 disposal value chain. Without a plan for storing the CO2, there you really can't have a capture project. And we talked about that capture step, the first panel on the left side here. And most of the cost and a lot of the engineering is tied up in capture. But unless a plant happens to be located directly above a disposal well, you need to arrange for the transport of CO2. This isn't new. We already transport CO2 by truck, by rail, by ship, and by pipeline for things like making fizzy drinks, and as Roger was saying, for enhanced oil recovery. Pipelines are by far the cheapest way to move CO2 at the scale required for CCS on power production. And as Roger noted, there's only a few pipeline networks here in the US. We're also seeing ship-based networks appearing in the Nordics of Europe. So that's the transport piece right in the center. The final resting place for CO2 is in a disposal well, thousands of feet underground. And as Roger said, here in the US, we can drill those wells and we can be very confident of long-term CO2 storage in places in the Midwest, in California. Uh, Wyoming's got great storage, and certainly the Gulf Coast off of Texas. The design and construction of these wells are regulated by state and federal environmental authorities. That's the Class 6 CO2 disposal well permitting infrastructure. And right now, because there's limited pipeline infrastructure, developers of CCS projects for power production on natural gas power plants need to partner with a reputable Class 6 well developer to ensure that the disposal well will be ready to accept CO2 by the time the power plant comes online, because if you have nowhere to put your CO2, you have no CCS project. So we'll go to the next slide, and I'll go through really quickly some of the key things that you might expect. Bottom line up front, how much is it going to cost? The answer is that it depends. It depends on whether you're combining CCS with a new plant or retrofitting, and where you are in the country, how far you might need to transport. Um, a lot of study has been done on this. A lot of that was done in the mid 2000s, the early 2010s. And so some of the numbers here are from studies that were done a while back, before we started to see some substantial inflation over the past 3 or 4 years. But take the relative numbers and apply them to how much you think it would cost to generate electricity from natural gas. What we anticipate is that delivering electricity with the CO2 emissions abated with CCS will be about 50% more expensive than electricity from natural gas without CCS. Um, I mentioned that it takes energy to run all of that equipment. From an energy point of view, you sacrifice plant efficiency when you add CCS. You lose about a fifth of the electricity output. If you think in terms of heat rate, it means your heat rate goes up by 20%. If you think in terms of thermal efficiency, it means your thermal efficiency drops by 7, 8, 9 points, go from 50% to 42%. But you do need to power the equipment. But when you invest all that extra money in the equipment and you run it, you get 90, 95, potentially more than 95% less greenhouse gas emissions coming out of the power plant itself. That's enormously beneficial to the climate over running the plant without CCS. Stack emissions aren't the only story. There's definitely upstream emissions associated with the production and processing and distribution of natural gas. That would take place whether you have CCS or not. But if you're buying power and you're concerned about climate, it's definitely something to watch. Since CCS doesn't address those upstream emissions, we think CCS will give you an overall system impact of about a 75 to 80% reduction. That could be better with responsibly sourced natural gas. And we think we can bring these plants online within a few years. We know from back in the early 2000s that with a well-functioning supply chain, you used to be able to build a new natural gas-fired power plant in under 2 years. But all the planning needed to build, capture, transport, and storage means if you're starting from a clean, but if you get to a final investment decision, it's probably going to take somewhere of the order of 3 to 4 years to get a plant online. And as Roger said, these plants want to be big. The economics of moving that much CO2, storing that much CO2, and so on really favor plants in the 100 megawatt to 1 gigawatt range. Um, so, uh, this is appropriate for large baseload or maybe even deliberate sort of load following mid-merit plants, which is a great match for the kinds of loads being proposed by the companies building massive new data centers or really trying to fill out the demand for clean, firm power. And that's what it's like in theory. I want to turn it over to our colleagues from Calpine and talk about what it's like actually trying to put this into practice.
Thanks, AJ. Appreciate it. Can we go to the next slide, Sarah? So I first just wanted to introduce Calpine to those that maybe aren't as familiar with our company. So we're an owner and operator of power plants all over the country. The majority of our power plants are either natural gas or geothermal, although we recently have been deploying battery storage. We recently brought online a 680 megawatt project, one of the largest in the world in Southern California. But we own 79 power plants, about 27,000 megawatts of capacity. That's enough for about 27 million households in the U.S. And we have our smallest greenhouse gas footprint amongst our peers. We also have a fleet of combined heat and power or cogen projects that are able to, very efficiently serve our industrial customers as well. And as I mentioned, I've got a picture in the bottom right of one of our geothermal plants. We've got 13 geothermal power plants in Northern California that sum up to about 725 megawatts, and we call those as a group the geysers in California. In addition to that, we also have an integrated retail platform. So we've got Calpine Energy Solutions, which is our kind of serves our large industrial and kind of customers, our larger customers with more bespoke products and risk management services. We've also got our residential and mid-market brands of Champion and North American Power serving customers in 23 states. Go to the next slide, please. So here is our fleet. We divide ourselves into three regions. We've got the West, Texas, and the East. I'll take a moment here to kind of point out, where a lot of our carbon capture development projects are. So right now, we've identified 12 projects between Texas and California, which both happen to have great geology, by the way, and in addition to some existing CO2 infrastructure pipeline network. Across these 12 projects, we could reduce about half of our carbon footprint across our company. So 12 out of 79, they're large and they operate a lot and they have a big impact on our overall carbon footprint. I'll point out our geothermal. We're certainly looking to expand our geothermal facility. We did a 25 megawatt expansion last year. We're looking for different ways to expand that facility. And then battery storage pipeline. We've got a couple gigawatts in our storage pipeline, and I think we've got about a gigawatt operating online so far today, mainly in California. Lastly, we've got three, I mentioned we've got a pipeline of 12 carbon capture projects. We've got three that are kind of front and center that we've got our most aggressive development efforts on that we're moving forward pretty quickly. Next slide, please. Okay, so diving into CCS, I just want to take a minute to just give a little bit of history on our efforts that we've done in the carbon capture space. So we've been working on this for about 10 years now, as of 2026. We started in 2016 with early exploration of piloting efforts. We did a calcium carbonate pilot in California to look at making lightweight concrete aggregate for like parking lots and building structures. We really got serious about it around 2019. We did a really detailed study on the most efficient way to decarbonize our fleet. At the time, hydrogen was getting all the headlines, and that was actually, to be honest, the original focus. But as we dug deeper, we realized that hydrogen really wasn't all that effective, and it wasn't economic. It's effective, not as economic for displacing our CO2 footprint. And really, carbon capture and sequestration was going to be by far a better route to take. So we started jumping in 2019, did a full pipeline review in 2020, selected technologies in 2021, did a couple of detailed engineering studies in 22 and 23, and got really excited when we were selected for DOE awards in 2024 for demonstration projects, $270 million a piece for California and Texas. Those have since been terminated and are under appeal, but we're not slowing down. We're continuing to move those projects forward. So we've been doing a lot of feed studies and a lot of value engineering, and we're really targeting FID on our first project, hopefully first quarter of 2025. Next slide, Sarah, please. Okay, so maybe just a little bit of a different flavor of why CCS, right? And so you'll hear this term, firm, dispatchable, clean, and I would add the term non-duration limited, right? So that a firm, dispatchable, clean, non-duration limited resource is really important for the decarbonized grid of the future to maintain reliability. And so right now we've got three types of resources that fit that description. We've got nuclear, we've got geothermal, and we've got natural gas with CCS. What I plot on the left side here is kind of recent experience in each of these three types of resources. Of course, nuclear, the most recent nuclear plant to come online was Vogtle. It was about $15,000 per kilowatt. Going forward, relicensing of existing nuclear facilities, of course, will be less expensive. We have high hopes for SMR technology, probably in the 2030s that will be less expensive. But if you want something today, this is going to be the cost of what it's going to be for a new resource. Geothermal, we love geothermal. We've got a huge geothermal portfolio. We're looking to expand it, but that is very geology limited, right? So if you don't have the heat resource close to the surface, it's very difficult to make geothermal work economically. You can always go deep enough and eventually get the heat, but the dollar per megawatt hour goes up, kind of exponentially the further down you have to go, just given all the losses and efficiency of extracting heat from so deep in the earth. So geothermal we love, it's just not as broadly applicable. And then we get to CCS, right, which is probably the cheapest on a dollar per kW, but also much more widely deployable. So you do need some, proximate geology. Thankfully, in the U.S., we've got great geology, broadly, really great in Texas and California, all along the Gulf Coast. And there's other areas of the country, West Virginia, for example, that have good geology as well. Not applicable everywhere, but very broadly applicable. And we're excited about it. The other great thing about CCS is it is retrofittable, as Roger mentioned, to existing assets. So the majority of our efforts to date have been focused on retrofits. The 12 projects I mentioned up front were on retrofits. Of course, we're open and interested in doing greenfield projects too. But really, the exciting thing about this technology is that it can kind of do both new and existing assets. Go to the next slide, Sarah. So, I wanted to talk a little bit about, the need for a clean, firm, flexible, non-duration, limited, power. And so I've got an example here of just kind of like maybe two different ways to think about power supply in a grid that is going through a decarbonization. Um, on the left side, I've got the carbon attributed to 100 megawatts of around the clock load if you were going to serve that load in three different ways, or you're kind of a buyer thinking about three different options, right? So the gray bars, if you just bought from the grid, this is California. And so you just bought around the clock grid power 2018, 2021, or 2024. In each of those years, you'd basically be creating essentially or attributed 300,000 tons per year of CO2 to that load that would be required to produce electricity, to serve that load. Option A is if you were to buy, 100 megawatts of solar to offset, or sorry, the equivalent energy to offset that 100 megawatts of load from solar RECs, right? So you basically be buying, probably 300 to 350 megawatts of RECs because they're only operating at like a 30% capacity factor. But you're basically buying the equivalent number of RECs to serve that load for the entire year. Back in 2018, before the grid was saturated, that was a pretty effective strategy. You'd reduce about 75% of your carbon by buying RECs in the middle of the day to serve your 24/7 load. Over time, as we've installed more and more solar in California, that strategy has become less effective. At this point now, when you add more solar to California, we're offsetting other solar a lot of the times, right? And so at this point, incremental solar in California is becoming less effective. You're still getting some kind of carbon benefit, but your bang for the buck isn't nearly what it was, 6, 7, 8 years ago. By contrast, an alternate way would be to put 100 megawatts of carbon capture either on an existing asset or a new asset, in which case that carbon benefit, and if you're serving that load with that firm, flexible resource, that carbon benefit is consistent and durable, since you're not kind of counting on a time mismatch, but you're actually serving the load as it's needed. You're matching it 24/7, and you're able to reduce the carbon in every hour to get that kind of 95% benefit. Moving to the right side, just to kind of illustrate, maybe more of this dynamic in the California market. And I'm using California as an example because there's a lot of solar and they've been kind of a leader in this area. But any grid that's kind of saturated will have a similar dynamic. But on the right side, we're showing this is spring of 2024. We picked an example day in 2024 when it was a mild, sunny day. Solar, load wasn't super high, and but the solar generation was high given that it was sunny. The bars are the solar generation, so it got up to about 11,000 megawatts in the middle of the day. And the line is the power price, the local power price in that area. So you can see the power prices went down to about negative $75 for a good chunk of the day, meaning that the solar generators were paying the grid $75 to allow them to generate power in order to earn the REC that they needed to earn contractually, right? They were obligated to generate these RECs. What happens in a situation like that is the grid is redispatched and other resources are sub-optimized, and actually results in a day like this, you actually end up with a higher carbon footprint because of the kind of sub-optimization of the grid from this distortion of negative pricing. So just making the point that really, at the end of the day, a firm, clean, dispatchable resource that meets the load when it's there is required the deeper the grid gets decarbonized. Early in the decarbonization, it doesn't really matter. but later on, it becomes very meaningful. Next slide, please. So a different way to look at this. So what we have here is there's been a bunch of public studies on what does the deep decarbonized grid of the future look like. A lot of them use 2050 or 2070 as kind of their example. You're gonna say, hey, if we want to reduce our CO2 by pick your number 95% by 2050, what does the grid have to look like? And each of these studies ran two scenarios. One of the scenarios was we're going to allow the building of new clean firm resources. So CCS is an example. It could also be nuclear, geothermal, but something that's not duration limited, that's clean, firm, and dispatchable. The other scenario that they ran was, what if we did it all with renewables and batteries, right? Short duration batteries and renewables, and we didn't allow any new clean, firm, dispatchable resources. And basically, what we've plotted here on the left, we normalized them all to 100 megawatts here, 100, pick your unit. I guess we just said 100 megawatts. So the clean firm resource, if you need to build 100 megawatts for the grid of the future, if you allow clean firm resources, all the other bars represent the multiple that you'd have to build if you don't allow that clean firm resource to be built. So anywhere from 6 times to 11 times as many megawatts need to be installed on the grid if we exclude like a nuclear or carbon capture and storage resource. If you try to do it all with renewables and batteries, you end up with massive, massive overbuilds of the grid. So these studies are public. Probably the most famous one on here is the Princeton Net Zero study, the one that's on the left side. So I encourage you to look that up if you want to read it. On the right side, we show the transmission build out that's required, for a grid of the future that looks like this. So the top chart or the top picture shows our power grid in 2020. The bottom grid shows, kind of a renewables only grid in 2050. And probably the most impactful thing is just to look at the coloring, right? The grid on top, you can kind of see some lines, going across the various states, and the grid on the bottom is almost solid colors, right? So, but it's a 400% increase in transmission capacity compared to what we have today, and $3.7 trillion of cost to build that grid. So, point being, we need some type of clean, firm resource. We believe carbon capture and storage is the most economic and commercially deployable resource today, which is why we're so focused on it. But we need something that gets us into this grid of the future. Next slide, Sarah. So lastly, I just wanted to make a plug. I mentioned up front, we did a pilot on an actual operating, combined cycle facility in Northern California at our Los Medanos facility. We did it in partnership with Ion Clean Energy and the Department of Energy. We ran that pilot for more than a year. It's still sitting out there. And we decided at the time, we had so much interest in the pilot and visiting the pilot that we actually built a learning center. So we've got the Carbon Capture Learning Center in Pittsburgh, California, pretty close to San Francisco Bay Area. And to date, we've hosted 70 tours, over 1,000 visitors, and we're happy to host groups that are interested in this. So to the extent you have interest, you have a group that has interest, feel free to reach out, and we'd be happy to host you. So with that, I think I'm hopefully not too far over time, and I'll pass it back to Roger for the next topic.
Okay. All right, sir. Next slide. Okay, so let me just talk a little bit about what, from a buyer perspective, what transacting for CCS would look like. Certainly, there's a lot of similarities to how companies are used to buying clean energy today, wind and solar. The tools really are basically the same: PPAs, VPPAs, utility tariffs, attribute-only transactions. All that can be applied to CCS. So we're looking at kind of typical, well-known transaction types. And there may be a need and some interest in some non-standard structures, which we've seen used for other technologies. We've seen it in the CDR context, and that might be an advanced market commitment of some kind to help deal with some of that early risk. Again, because of the size and also because of risk mitigation and distribution, you might have multiple pooled offtake kind of structure for a facility. There is significant private capital out there that's looking to deploy in clean energy solutions as part of their mandate. So there might be opportunities to partner with private capital to help bring down costs. So those are a little differentiated approaches. There are some things that are very unique to CCS when it comes to thinking about how you would contract for procurement. First, as we've discussed, these are not zero emission megawatt hours. They're low emission megawatt hours. and the associated attributes and emission rates, therefore, that go with that power are not going to be zero. I'll get to the greenhouse gas accounting piece of that in a second, but that's a difference for sure. The other big difference here between wind and solar, you have no price, you have no fuel cost, and you certainly don't have fuel price volatility. Well, you do here because you are exposed to natural gas markets. So there'll need to be some hedging structures and adding a little complexity to, unfortunately, already complex transactions like virtual power purchase agreements. But ultimately, that's all manageable. But again, it is different. Yeah, go ahead, Sarah. I'll come back to the greenhouse gas accounting stuff. Policy. So let's just go to the incentive and the regulatory side. On the regulatory side, AJ's covered some of it, but let's go back to the incentive side. The 45Q tax credit. 45Q tax credit, fun fact, it was the first federal price on carbon ever signed into law, and that was signed into law by Donald Trump. And it is also one of the few clean energy policies that survived the One Big Beautiful Bill. In fact, it was strengthened. So 45Q is on pretty solid political grounds with bipartisan support, and the kind of scary cost numbers that AJ talked about earlier, which I think you said, AJ, translates in CCS to around $100 a ton. Well, with 45Q, you have an $85 a ton subsidy. So this is a significant piece of the capital stack. And it is designed to not reach parity in pricing to uncontrolled gas, but it certainly goes a long way. State and federal regulation of storage, Safe Drinking Water Act, Clean Air Act. There are pretty extensive regulations at both levels on how you do underground storage, how you manage these wells, Class 2 and Class 6 wells. And if you're claiming the 45Q tax credit, there's an extensive regime for MRV on an ongoing basis. Footnote, that regime is a little bit up in the air right now as the EPA is repealing the greenhouse gas reporting program, but we expect that the piece on monitoring and verification from Class 2 and Class 6 wells will otherwise show up in law, and we expect that to continue. Okay, I think next one is my last slide, and I'm just going to hit this on a high level because it gets a little bit complex, but greenhouse gas accounting for CCS. So today, we do not have energy attribute certificates in the marketplace for CCS power. Nonetheless, the Greenhouse Gas Protocol and Scope 2 rules do allow a buyer to reduce their Scope 2 inventory by buying clean energy, even if it does not have an associated instrument with it. So we have a way under existing rules for a buyer to account for their reduction in their Scope 2 inventory from procuring from a CCS project. You also, different again than wind and solar, you have kind of multiple pieces in the CCS value chain where there are emissions, and how do you account for those? We think it's relatively straightforward, even though not explicitly laid out in any guidance at the moment, that all the emissions from inside the fence line at the plant, which will include both the residual CO2 and the flue gas, that 5 or so percent, and then any emissions associated with operating that on-site equipment. All that will go into the emissions rate of the power, and that emissions rate becomes the basis of your Scope 2 claim. Emissions outside the fence line of the power plant, talk about downstream, the downstream emissions associated with transport and the injection. Those are clearly Scope 3 to the power plant, and they're going to be Scope 3 to the buyer. In terms of upstream methane emissions, they are already considered Scope 3 today, and there's no change there at all, whether a plant has CCS or doesn't have CCS. Certainly transactions, transparency, liquidity in the marketplace around CCS transactions will be aided by a robust attribute market. And there are efforts underway as we speak to develop an EAC for CCS and to determine how to put that into the larger attributed infrastructure, registries, and trading platforms and so forth. There's some questions that are going to need to be answered there. Again, it's different because it's a non-zero emission rate attribute. There's a further challenge there in figuring out, well, what is the actual capture rate? For any given plant, that capture rate could vary for various reasons. So we need to figure out how to, when we stamp that megawatt hour of CCS energy, how we determine, apply, and disclose in that the capture rate, which goes right to the emissions factor that the buyer needs for its scope 2. And there are discussions of other information that should be added to an attribute, how the CO2 was disposed of, and some other information there. This is not information, essentially scope 3 information. It's not included, obviously, in a REC. So there'll be some ongoing discussions about that. All of this is couched in a bit of uncertainty of the moment because we have the Greenhouse Gas Protocol Scope 2 guidance under review, and because SBTI is in the midst of an update as well. And there are CCS-related question marks associated with all that, and I'm very pleased to have someone else describe that to you, and I'm going to pass it back to Sarah.
Thank you. So you just heard a lot about some very important reasons to consider CCS as CEBA, as an organization focused on global electricity systems that are decarbonized. We want to ensure that energy customers are also recognized and able to account for action related to uptaking CCS. And so 2 areas to call out right now. Roger just mentioned the Greenhouse Gas Protocol and SBTI. There are open comment periods for both, and we encourage everybody who's on this call and anybody who's watching the recording in the future to participate in those. The Greenhouse Gas Protocol has just moved back their response deadline, thankfully, to January 31st. As Roger said, there's not a specific CCS mention within the Greenhouse Gas Protocol as far as a way to provide feedback in the survey. It certainly use some of the open response areas. More generally, we encourage you to scan that QR code, check out our toolkit if you're interested in the Greenhouse Gas Protocol response. We have some materials for you. Directly related to CCS, the SBTI net zero standard, which is also currently open until December 12th, so that's next week, has some criteria or elements to the standard that will, we think, have impact on uptake of CCS for energy customers. 3 specific areas: 1 around the age limit from the generation facilities being 10 years. Importantly, the second one, assuming a 95% carbon capture rate. You heard AJ say that there's a range right now, 90 to 95%. Assuming a 95% at the beginning would really undercut the technology's ability to scale and improve over time. So that one's one to note. And then thirdly, the hourly matching and physical deliverability requirements would take out some of the market-based mechanisms that allow customers to participate even if they're not physically receiving that energy. Those 3 areas we find would be really important to weigh in on if you have designs on CCS, are an SBTI member, although it is open to SBTI, anybody can respond to the SBTI response. So there's a link in the chat to our public consultation toolkit that has a QR code. We are also developing a toolkit for the SBTI. So if that's something you would like to receive from us, my colleague Carrie will be eager to hear from you. Her email is there in the chat and also on the slide. So all this to say, all these things you just heard about from AJ, Roger, and James, the compelling reasons to consider CCS, the urgency in which we need to, look at these new technologies, and the kind of first of a kind, first mover challenges. We need to find ways to incentivize and recognize those energy customers. So with all of that, I'm going to skip the details here. I'm going to drop our emails for everybody who's been speaking. We really encourage you to reach out to us. And now is an opportunity for you to think about a couple questions that you might have and drop them in the chat. I'm going to throw one back to AJ, Roger, and James while you all think. You can either come off mute when you're ready or drop them in the chat. For Roger, AJ, and James, just as you think about the energy customer opportunity related to CCS, what's kind of one key takeaway you would, or what's one thing you would say to an energy customer if you were advising them now and they came to this call, they're interested in understanding more, where should they go next?
Why this should be enticing. It does offer great volume. So if you're a large customer and you want to take a significant part of the attribute and energy output of a CCS plant, it's a way to get a whole lot in one transaction. And as you all know, an offtake contract is expensive and difficult, regardless of its size. So there's some efficiencies there in what you get. Some companies have a mandate or interest in directly incentivizing and helping bring to market new technologies. This is a very important one to do that. And where to go? SEBA will be a great repository of information on project development and how to transact. And you can always rely on SEBA. If you haven't joined SEBA, you should.
Sure. I'll follow that up, Roger, with, letting the folks here know that natural gas power with CCS is it is a premium product, much like solar and wind power were 10, 15, 20 years ago. And it was the members of SEBA, the folks who were out on the front lines, who really brought that zero carbon power to bear. They enabled what was much higher capital cost equipment to get out there and deliver fuel-free, zero marginal cost electricity onto the grid. And that was really important for the climate. It is really important for the cost of electricity. And times have now changed, as James talked about. And that next premium product is this clean, firm power. And as James said, natural gas with CCS is how you get 90%, 95, potentially 98% clean power that's available 24/7, which is the thing that is going to support a sustainable, reliable, and cost-effective grid going forward. So this is a call to action for those same folks who were out on the front lines, bringing the last generation of clean and affordable power to bear, to lean forward and bring the next generation into the grid. And as Roger said, the SEBA community, particularly the fact that the SEBA community is made up of both clean energy buyers as well as clean energy project developers, is an important place to get information. Roger knows a lot about this stuff. Go talk to Roger. And we at Carbon Direct love helping people navigate navigate the clean energy space, the carbon management space, and ultimately the carbon removal space. So come talk to us as well.
And you guys did a great job. I'll just add one more point, which is just kind of thinking towards, moving towards an hourly matching mindset. And for serving your load, I think makes a lot of sense in terms of actually having the carbon reduction impact that you're trying to have. So not, buying power that's produced in one type of day to offset emissions in a different time of day, but actually matching it hour by hour is very impactful and will continue to be more impactful the deeper we decarbonize the grid.
Thank you all. I see one question from Michelle in the chat. So for anybody who's on the phone, I'll just read it out for you in case you can't see that one. So Michelle asked if there's a higher demand for carbon capture, if there was a higher demand for capture carbon in other industries like manufacturing, how would that impact push for carbon capture? How can we market carbon as a commodity?
And I can take a first swing at this one.
Yeah, go ahead, AJ.
CO2 is already a commodity. It's just not traded and managed at the scale that we would need to use to manage to make a real dent in the CO2 emissions coming from power production. So we manage CO2. I don't have the numbers off the top of my head, but I think it's like 25 to 40 million tons a year here in the US in the merchant CO2 market. Again, that goes into anything from, fizzy beverages to dry ice to refrigeration systems and so on. And then a lot of it is also used, as Roger said, for enhanced oil recovery. Um, Making products out of CO2, making products that aren't CO2 out of CO2, like the CO2 in your fizzy drink is carbon dioxide. The CO2 in your dry ice is carbon dioxide. The CO2 that's used as a refrigerant is CO2. Using CO2 as an ingredient chemical, reacting it to make other things actually takes a lot of energy. And so while there are some really cool and innovative technology companies who are trying to push the boundaries of that and find even bigger demand for other carbon-free energy to turn CO2 into value-added products, that is a technology space that I think is likely to grow more slowly than our need to manage bulk CO2 and dispose of it at scale to meet the climate imperative. But
Yeah.
with that said, there is still an opportunity to put a substantial amount of captured CO2 into the merchant CO2 market and thereby offset some of the other places we get CO2 from, which are non-sustainable.
Yeah, and I'll just say in general, yes, there's captured CO2 and there's uh, other CO2 which comes with a heavier carbon footprint. But generally, more demand for CO2 hopefully increases the price, which improves the economics of a CCS plant. Let me just say one other thing I should have said in response to the last question, and from a buyer perspective on why there might be interest in this. We may be moving towards, I think we are moving towards, but the speed at which this change happens is unclear, towards a consequential disclosure, consequential accounting world where buyers will become interested not just in the attribute that comes to them that expresses an emissions rate, but also what was the real world impact of the generation that you're buying in terms of displacement of emissions. And for wind and solar, that becomes kind of a marginal emissions analysis, and it gets a little complicated. CO2 is very straightforward. CCS is very straightforward. You can capture that carbon, you can count that carbon. It was on its way into the atmosphere, and because of the project and because of your offtake, it no longer is. So it's a very straightforward calculation of consequential impact.
Great. Thank you all. And with that, we are at time. So I appreciate all of you joining as participants. Appreciate all the folks who are here as listeners. If you're interested in finding out more from SEBA and getting in contact with us, in addition to our emails, here's how you can find us as an organization. We have lots of upcoming events. Happy to connect with you. somewhere in the world. So thank you all again. I will distribute the slides and the recording to everybody who registered. So if you want to go back and dig in on any of these nuggets, you will have the opportunity. Have a wonderful day.
Thanks.